So suppose you have a group acting on a set X. Then there's a nice equivalence relation you can define. Given X and Y and G, we're going to say X is equivalent to Y with respect to G, so they call this G equivalence. If and only if X is equal to G dot Y for some element in the group. You can check that this is an equivalence relation. Due to the history with group actions with cyclic groups, the equivalence classes are called orbits. So that's the fact. They're called orbits. And so another interesting one you can look at is the notion of a stabilizer subgroup. So that's the orbit. Parallel to the orbit is given X in your set. The stabilizer subgroup that fix that element. Now, one of my favorite theorems involving group actions is the following. Let G act on a set. Then the order of G is actually, well, and let P be an element in X. Then the order of G is given by the size of the orbit of P. So the size of its equivalence class under this equivalence relation times the size of its stabilizer. So for instance, consider a cube and its symmetries. Now you can see that the symmetries, so we're going to let SC be the symmetry group of the cube. They permute the vertices, the vertex set of the cube. And it's not too hard to see that given any vertex of the cube, any two vertices of the cube, there exists a symmetry where sigma of u equals v. You can try it if you really want to. Just get out a cube, pick your favorite point, pick another favorite point among these 8 vertices, and figure out how to move from one to the other. It is in fact possible. That's enough to tell you that the size of the orbit of u for any vertex has to be 8. Because literally every vertex is in the orbit, and there's 8 vertices. Harder to tell without actually getting a model is to see that there's a 120-degree rotation given by holding this vertex still and its opposite vertex and spinning so that this red vertex goes to this blue vertex, which goes to this green vertex. And that symmetry fixes this vertex, so it is in the stabilizer. and its inverse does too, and so does the identity element. And so it turns out the stabilizer of a vertex has order 3. And so 3 times 8 is 24. And so it turns out this group has order 24. Of course, it's possible to end up proving that it's actually S4 itself by actually looking at the diagonals between opposing pairs of vertices. There's exactly 4 of them, and you can end up proving that each symmetry corresponds to a permutation of those 4 diagonals. But you might not have known to even try that without knowing in advance what the order was. You could actually use this to rederive other orders we already know, for instance the dihedral group. If you take a vertex on your polygon, it's easy to see from rotating that you're going to be able to get from any vertex to any other vertex. So the size of the orbit of a vertex is n. It contains every vertex on its orbit. On the other hand, what is the size of its stabilizers? Well, there's only 2 symmetries that fix a vertex. The identity symmetry that fixes every single vertex, or the axis of symmetry that goes through this vertex. And so the stabilizer always has order 2. And so we see the group has order 2n, like we've already seen before. As one final example, you can look at Sn, which we just saw was a group action. It acts on the integers 1 through n. I'm actually going to just pick on n this time, specifically. It's easy to see again that the orbit is everything, namely because the permutation in exists, and that permutation sends n to I and leaves everything else alone. So there is a permutation that sends the number n to everything else. So everything is in its orbit. And so that's true. And so we need to figure out the stabilizer. So what's the stabilizer? It's those permutations that fix n, which means n is a 1 cycle, which means that you can just pretend that you're working with Sn minus 1 by just ignoring the 1 cycle. And so whatever this group is, it's the size of Sn minus 1. And therefore, the size of Sn is n times S sub n minus 1. Which means by induction, you get n times n minus 1 factorial, you get n factorial, like we already knew. So there's another proof of that fact. Finally, as one last definition, is the fixed point set given a group element. X sub g is the is the set of fixed points. So it's those elements in X such that g dot x is X. So note the difference here between the stabilizer. The stabilizer are the group elements that fix a given point, whereas the fixed point set are the set of points that are fixed by a given group element. So the difference here is whether you're looking at varying x for a fixed g or varying g for a fixed x with this one equation. And so one reason why this is considered important is Burnside's lemma, which is actually not originally due to Burnside. It's a long, complicated story. If G acts on a set x then the number of orbits is given by 1 over the order of the group times the summation over every element in the group times the number of fixed points. So if you've taken statistics, this would be what you would call the average number of fixed points. So the number of orbits is the average number of fixed points. And as we'll see in later videos, this is a useful formula for solving certain types of counting problems, because you're counting these equivalence classes, and this gives you a way to do it.